Okay, so parallel circuits. So series circuit, just to remind you, series circuit looks like this. Okay, where you have things that come right after each other, right? They're going to come one right after one another. The parallel circuit looks something like this. Okay, well, when you look at the circuit, you have each resistor comes one after the other. Sorry, not one after the other, but they're connected. So if you notice here, this end is connected to this end on this side. This end is connected to this end, and then this comes back to the battery. These, each side of the resistor is connected to each side of a second resistor. And if you have a third one, each side is connected to the third one over here. So unlike this where they come right after each other, these you can think of as happening kind of at the same time. So they're parallel or happening concurrently, each path. So this is our parallel circuit. So if I put a voltage here, let's compare with yesterday. So we had our voltage here, we had a resistor here. How much was this resistor? 10 ohms, 20 ohms, 30 ohms, right? So we have our resistors, 10, 20, and 30. Okay, and now what I would ask you to do again is to kind of solve this circuit, to simplify and solve it. So yesterday with series, let's just have on the side what our series circuit VIP look like. So we have a comparison. So we have 10, 20, 30, right? This was for series. And let's just get our numbers from yesterday. What was the current? Someone that has their notes open. What was the current from yesterday? 2? 2 for all. So remember, a series, everything has the same current. What was our voltage? 20, 40, 60. And our power? 40, 80, 120. Okay, so that's going to be, that was yesterday. So let's compare. We're going to do the same thing as we did yesterday. So as we have here, we have a complicated 3 resistor circuit. We're going to simplify it to the simplest. This is called finding the equivalent resistance. So we're going to try to find the equivalent, which means how many resistors? 1. So we want to create one and only one resistor that is the equivalent to this 3 resistor combo. Okay, so we'll call this V, we'll call this R equivalent. Now as it turns out for parallel, okay, the way you find it is not quite as easy. The equation to find the equivalent for a parallel circuit looks like this. 1 over Req equals 1 over R1 plus 1 over R2, 1 over R3, etc. So in other words, you sum up, it's not merely summing up, you're summing up the reciprocals. Okay, summing up the reciprocals. So let's just see what happens. Let's go ahead and do this one. Let's see what happens when we do this one. So 1 over Req equals 1 over 10. So please try to do this in your calculator. Actually, this one you could probably just do fractions. It's easy enough, but do it with your calculator. It takes people at least 1 or 2 tries before they can feel comfortable doing it. So my recommendation is add up all these. 1 over 10 plus 1 over 20 plus 1 over 30. Get yourself a number. It's going to be some small decimal-y type number. So like 0.183. Okay, however, that is not the answer. So this is 1 over Req equals the 0.183. So you have to then reciprocate that number. Okay, take the reciprocal of that number and we get like about 5, right? 4 or 5? Okay, so that's our equivalent there. So first of all, let's take a step back. What do you notice about that number? It's kind of weird compared to series. In a series, remember, what did we do? We just added them up. 10, 20, 30, that's 60. Okay? Resistance went up. What happened here? Resistance went down. Okay, resistance went down. And what that means is as we add resistors, so for example, if we just started with 10 ohms, it would just be 10 ohms, right? If we add another resistor, it actually decreases the resistance. And if we add a third resistor, it even decreases it even more. Okay? So why does that happen? Anyone think of conceptually why adding resistors actually decreases resistance and not increase? No one wants to get on tape or on video. So anyways, think of it this way. Imagine this was a cars, like cars on a road. So if you're in a series circuit, how many lanes do we have in our road? One, right? One and only one path. In a parallel circuit, how many lanes do we have? 3, okay, or 3 loops here. Think of it as 3 circles or 3 loops. And so what that means is, well, think of it with like a road. If you have one road, one lane, there's going to be a lot of traffic. You're going to have high resistance. If you all of a sudden went to 3 lanes, resistance goes down, right? And there's going to be easier for you to go through. There's going to be a greater traffic flow. And so that's kind of the same concept here. By adding more paths, if I were to add a 4th path, what would happen to the overall resistance? It would decrease. So adding more resistors decreases resistance in a series circuit. Okay, so let's keep going. So remember, the purpose of finding equivalent is to simplify our lives, simplify the circuit, right? So this one is, this was 120, right? So the voltage is going to stay the same, 120. And so now we can solve this circuit, right? We can go ahead and solve this circuit right here. So we can go use Ohm's law, V equals I times R, or I is V over R. 120 volts, 5.45 ohms. Is that 22? Okay, so that means 22 amps. So this would be like my I total. I total of the circuit equals 22 amps. Let's find P total. How would we find P total? I times V, yeah, so we'll just go 22 times 120. Gives us a big number.
2,600.
Okay, 2640. So that would be our total power, right? Our total power for the circuit, all 3 bulbs. Notice, compare that just with series real quick. What was our total power series? 40 plus 80 plus 120, 240. So it's dramatically different, right? So it's a big difference. Parallel circuits will always produce more power than series circuits. Okay. Alright, so this right here, if I were to draw on my current, I would get a 22 amps would belong right there. And then what we're going to do is we got to figure out where does 22 amps belong on our original circuit. Because remember, this is where we're trying to get to, is the original circuit. So what do you guys think? Where does 22 amps belong on our original circuit? Here's one option. Does 22 amps belong down each branch? On a series circuit, that's what happened, right? Everything got 22 amps. So one of the ways to think about this is, remember this R equivalent here, this came from the fact that if we were to draw like a little box around this, All these resistors here are represented by this resistor down here, this equivalent resistance. So in other words, if I have 22 amps coming into this box, I must have 22 amps coming into this combination over here. So our 22 amps belongs right here at the beginning. It also belongs one more place. Where else? At the end, right. So coming out of this would be 22 amps. Coming out of this would be 22 down there. Okay, alright, so what we're going to do is we're going to go ahead and try to finish solving the circuit. I'm going to redraw this just because it's getting messy. Alright, so here's our circuit here. We have our 22, we have our 10, our 20, and our 30, 120, 22. Alright, so one of the other key components with this parallel circuit, and what I want you to notice is that each of these resistors, notice this end of the resistor is hooked up to our battery here. This end of the resistor is hooked up to the battery here. Therefore, what's the voltage drop across this resistor? This is hooked up to the battery, this is hooked to the battery. What's the voltage across this resistor? 120. Yeah, so it's directly connected to the resistor. So this would have a voltage of 120 volts. Okay, that would be my voltage across that resistor. So let's go ahead and do our little V. We'll do our VIP down here. 10, 20, 30. Okay, so for the 10 ohm, we just said it was 120. 120 volts. Alright, let's take a look at the 20 ohm. Notice the 20 ohm, just because there's a wire here, that doesn't change the fact that the 20 ohm is also connected to the 120 volts, which means how much voltage is across the 20 ohm? 120 volts. What about the 30? The 30 is also directly connected across the battery, right? So the 30 ohm is also going to be 120 volts. So in fact, all three of these are 120. And this is one of the characteristics about a parallel circuit. They will always have the same voltage, and if it's pure parallel, they would always have the input voltage, whatever the battery happens to be, or the voltage source. Okay, and so I could just do this by doing one big V here, 120 volts across the whole thing. Alright, so what are we missing? Currents and then powers. Once we get the current, power should be easy to find, right? So here's what we got to do. First of all, we can't have 22 going through each. What's wrong with 22 going through each? So think of it, let's use car analogy again. If we had 22 cars going down a one-lane road that opened up to a three-lane road, could we have 22 cars, 22 cars, and 22 cars? Okay, no. Okay, that would not make sense, right? We all of a sudden have 66 cars where we only started with 22. So they have to kind of split up that current. Some's going to go down here, some down here, and some down here. So how are we going to figure out how much go down, say, the first branch? We know the resistance, we know the voltage. How do we find the current? I equals V over R. So what we're going to do is we're going to use I equals V over R for each individual branch. So the first one was going to be 120 over 10, gives us 12. That means there's 12 amps going through that first branch. Alright, and then the second one, okay, we're going to go I equals V over R. So this is going to be 120 over 20. 6 amps going through this branch. And do it for the last one. 120 over 30. 4 amps through this branch. $12.64. Now there is a mini check you can make on yourself. What's the mini check? Okay, so we had 22. They should all add up to the total, right? If we have 22, 12 breaks off this way, 6 through here, and 4 through here. They add up to 22, and that'll always happen. So you can do that check. Last but not least, how we find the power? We just multiply them, right? So it's like 1440, 720, and 480. Okay, so let's look at the power results, compare them with the series results. Right, you have them off to the side here. They are right here. So what do you notice? Okay, yeah, it's much, much greater. So notice these are much, much brighter than these ones here. Okay, and what else do you notice? Which one was the brightest with the series? Okay, the highest resistance was the brightest, right? Which one was the brightest with the parallel? The lowest resistance. Okay. So remember, we talked about this yesterday. The series one, because they all have the same current, you have to look at which one takes up the most voltage, or which one has the biggest kind of energy drop here. And that's the 30. In this one, what's the same for all of them? The voltage is the same, right? 120, which means whichever has the smallest resistance should have the most current, right? Smallest resistance, more current's going to flow through it, therefore more power. Okay? So that one would be the brightest in that situation. Alright, any questions on just kind of how we set this up? No? Okay, I think I'm going to